just make sure I get them. And so we have the two balanced half reactions here. And we're combining these two balanced half reactions to get the net redox reaction shown here. This is a net redox reaction. So I see that some people got this as a net redox reaction, and then they canceled out the electrons. You know, the 4 electrons gained must equal to 4 electrons lost. We cannot have any electrons left over as reactants or as products. Again, if we had electrons left over as reactants, then we can't buy bottles of electrons. And if we have electrons left over as product, then we can't bottle those and save them. But there's additional simplification that can be done here. Do you see what else can cancel? Yeah, the 4H pluses. Do you see if we can cancel these? We have 4H pluses here, 4H pluses there. And then there's one more thing that can cancel. What is it? The water. I have 1 water here. I have 2, so I'll just drop this down to 1. And so we can do a little bit of extra simplification, and then we'll end up with this. C2H5OH is oxidized by oxygen to form acetic acid, CH3COOH, in water. So again, a lot of people said, well, you know, I got this equation, but I didn't have to go through all the hassle you did. Well, it's true. That was a lot of extra work that I did, but a lot of extra work saves me from having to figure out the oxidation states on all these. And I didn't see anybody successfully get all the oxidation states down. You know, some people started getting the oxidation states, but they were incorrect. And this is why I avoid oxidation state method, because a lot of mistakes are made in calculating the oxidation states. Okay, a lot of people don't have the rules down very well. So anyway, this is our reducing agent. This is our oxidizing agent. The other advantage of having the half reactions is so we can see the conjugates. And so here we have our reducing agents. This must be the conjugate oxidizing agent here. And if this is our oxidizing agent, this must be the conjugate reducing agent here. And so here, this must be our oxidizing agent, reducing agent. Since this reaction occurred, you know, and I have evidence that this reaction occurred because of the vinegar in the wine, we must be going from stronger reducer to weaker. And so that means ethanol is a stronger reducing agent than water, and O2 is a stronger oxidizing agent than acetic acid. This is weaker. So this is the driving force. I didn't have to determine that based on the chart, because that was just experimentally observed. You know, this is what happened here. So this is an example of a skeleton redox reaction where we don't have to predict the products. The major products are given. We just have to complete and balance it. The way we complete and balance it is just by following these steps here to make sure. The steps are in the book. The steps are in chapter 19 if you didn't get the steps. PowerPoint. All right, any questions on this?
So the final product would never show charges?
No. You could show charges. Yeah, because it's net ionic. What you end up with is a net ionic equation. The charges have to balance. The situation here is this. Just because the atoms balance does not mean the charges balance too. And so here, in order to make sure that this is truly balanced, we have to balance both the atoms and the charges. When we balance out the charges here, it's a bit more complicated. And I saw some people starting this. So for example, hydrogen is what charge? Plus. And how many do we have? We have 6. So we got those 6. And then oxygen is -2. Carbon is, well, we have 2 of them. For each one. What would it be for each one? No, it can't be +2, because +2 + 2 minus 2 gives me plus 2 plus 6 gives me plus 8. The whole thing would be plus 8. Can't be. Can't be plus. It's got to be minus. This is minus 2, this is minus 2. Then it works. Minus 2 minus 2 minus 2 is minus 6, plus 6 is 0. Ethanol has 0 charge. There's no net charge, right? The sum of the oxidation states is equal to the net charge of the species here. Okay, then oxygen here is 0, 0, and then we go through the same procedure and we make sure that the electrons, and then if you want to see this, actually, I don't want to go through this because I want to skip this method, but if you want to see this method, do they still show it here? Half reaction method, half reaction. The PowerPoints don't show it. An older edition of Kropelici had two sections for balancing skeleton redox. Balancing skeleton redox by oxidation state versus balancing skeleton redox by half reaction. The PowerPoints he has, he doesn't even show oxidation states because too many people make too many mistakes on the oxidation state, so I think that's why he got rid of it. And so it's much easier just to do it by half reaction method. So this is why I was asking for the half reaction. If you don't show me the half reactions and it's not a combustion, then I need to see this. You know, the hydrogens here, I have 4 hydrogens at plus. And I have 2 oxygens at minus 2. And I have 2 carbons at what? Two carbons at 0. And then over here, I'm going to have hydrogens at plus. I'm just going to go through this quickly because I don't have enough time. I need to move on to the next section. Okay, then when we balance it by oxidation state, we look at what happened to the carbons. Carbons went from a total of minus 4 to a total of 0. So that means it lost 4 electrons. And then what gained it? What gained it are the oxygens. And so I got to look at all the oxygens. This oxygen stayed the same. And so one of the oxygens stayed at minus 2, ended at minus 2. But 2 of the oxygens went from 0 to minus 2. That means it gained 4 electrons. Here's where we see that it's balanced. If this doesn't balance, then we have to adjust the coefficients until it balances. And that's more complex, I think, than this. This one requires a lot more thinking than that method. That method doesn't require that much thinking. It's just a certain sequence of steps that you do. Does that make sense? And so we have to do this. This is the same thing here. When I did this is a classic example that they give. Things could be, you know, some people will say this is balanced, but obviously it's not balanced because silver lost 1 electron, whereas copper, oops, I did. Silver gained 1 electron, sorry, but copper lost 2 electrons. Well, that can't be. We can't have one species gain, in other words, we can't have 1 electron gained and 2 electrons lost. And so what we have to do is we have to multiply this by 2. So we multiply by 2 and then it's balanced. Okay? That's the way you do it if you kept it